Welcome everybody to the seminars of the Departamento de Física de la Universidad de Santiago. Today we have Professor Will Kinney from the Department of Physics at the University of Buffalo of the State University of New York. He has been there as faculty since 2003. Professor Kinney received his Bachelor of Arts from Princeton University and his PhD from University of Colorado in Boulder. He has been a research associate and visiting professor at several institutions like Fermilab, University of Florida, Columbia, Yale, University of Chicago, la Universidad de Valencia also, and Stockholm University. His research focuses on the physics of the very early universe, including inflationary cosmology, the cosmic microwave background, dark matter, and dark energy. He is author of more than 70 published research articles and also is a very good teacher. He has received an award for excellence in teaching from his university. Today, he will give a pedagogical introduction to the theory of inflation as an extension of standard cosmology and discuss cosmological inflation in light of recent observational constraint and development in, we hope, quantum gravity in the future will be found or developed. Thank you very much, Will, again, for accepting the invitation. And you can now share your screen. It's all yours.
Okay, thank you very much for the invitation. It's a pleasure to be there, at least virtually. I'm sorry it can't be in person, but someday circumstances will permit proper travel again. Here I'm going to share my screen with the top slides. Here, so let's see. Everybody can see that fine? Okay, yeah. Good.
Very good.
Whoops. Okay, so let's back up. The person on the title slide you may or may not recognize. This is a statue of one of my favorite natural philosophers and scientists from the Renaissance, Giordano Bruno. And this is the statue of Bruno that is standing in Campo di Fiore, where he was burned at the stake for heresy in 1600. Among the doctrines which Bruno was required to recant in order to avoid his sentence from the Inquisition at the time were a belief in the heliocentric cosmology of Copernicus as opposed to the Ptolemaic cosmology, but also Copernicus was unique in that he took the Bruno is unique in that he took the Copernican principle, which we now have extended to the cosmological principle, the idea that there's no special place in the universe, and took it seriously enough that he was prescient enough to see that, in fact, there would be that Copernicus's ideas implied that the Earth would not be the only habitable planet in the universe. Bruno propagated a doctrine of what he called an infinity of worlds, that in fact there were many planets with many civilizations on them, and that the universe was filled with essentially an infinite variety of other habitable worlds. And what we'll see when we talk about inflation in the end of the second part of this talk is that in fact inflationary cosmology, which is what I'm going to give you a pedagogical introduction to, actually predicts a sort of radical extension of Bruno's idea of an infinity of worlds, creating an infinity of universes as well. And so I want to give you an overview of inflation, how it works, how it solves certain problems in existing cosmology, and then explore some of the consequences of that. And time permitting, at the end of the talk, I want to back up and start talking about the questions of embedding these inflationary theories in quantum gravity and some of the modern ideas that are coming up with respect to the string swampland and consistency of inflation with string theory, which is a real hot research topic right now. So let's move on. Let's get moving on this. We have a lot of ground to cover. So part one of the talk is the beginning of the world. I want to talk about the standard cosmological model. And probably one of the most consequential scientific developments of the 20th century was the realization that the universe had a beginning and the development of the standard hot Big Bang model for the universe. So the fact that the universe, in fact, has a finite age is something that has only really been recognized within the last 100 years or so. And it's a profound change in our view of how the universe is actually put together. So how do we visualize this? How do we understand how cosmic expansion works, and why does this imply that, in fact, the universe has a finite age? And I want to start with special relativity. So this is the familiar line element from special relativity that for most of you who are physicists will recognize this. So let me see if I can bring up a pointer. Can you see my, that pointer isn't real great.
No.
Let me see about, whoops, let's back up again. Okay, well, come on. I want to get rid of that text box on my, there, here we are. Okay, back. There we go. All right. So this is the line element. The ds squared on the left is your the proper time, the time that is measured by an observer moving along a world line through space-time, and t and x are the coordinate time, right? So this is the standard expression of the metric in Minkowski space, and this implies, of course, the existence of a light cone. So if we plot a space-time diagram with time on the vertical and space on the horizontal with one dimension of space suppressed, so that we have this is a diagram of a 2+1 universe, what we see here is that from any event in space and time that we'll call P, going forward from that, and light, if we measure light in the correct units, for example, if we measure the speed of light in feet per nanosecond, then the speed of light is approximately 1. It's about 1 foot per nanosecond, or 1 light year per year. And so we can draw light fronts traveling outward from an event in space-time as an expanding circle, where the outside of that circle traces out a cone with a 45-degree angle in my space-time. This should be familiar to most of you who have seen special relativity. And then a world line of an observer is a path through this space and time. As time moves forward and an object moves around in space, you'll see it trace out this world line. And world lines of objects, causal world lines of anything moving less than the speed of light going forward from this point P, lies inside this future light cone. And in order to travel outside this light cone along a path, for example, that's shown in this dashed line here, you would have to travel faster than the speed of light. And light always travels in this at 45-degree angles along this light cone. This is the familiar Minkowski space of special relativity. Well, how do we generalize this to an expanding universe, right? The special relativistic space-time, the light cone in special relativity is the space in special relativity, Minkowski space, is static and eternal. It has no dynamics to it at all. It has an infinite past, infinite future, and it is constant in time. In order to describe an expanding universe, however, we modify this Minkowski line element as follows by adding a time-dependent scale factor next to the spatial components, right? So this is how we code expansion into the metric of our space-time, is that we say these spatial coordinates that we see, all the spatial directions, have a time-dependent factor in front of them. So, and in fact, in an expanding universe, that time-dependent scale factor, A of t, is growing with time. So what we see is that the space is expanding with time. The spatial coordinates are getting larger and larger and larger. I think that I found that even among people who are fairly scientifically sophisticated, there tend to be a lot of misconceptions about the expansion of the universe, in the sense that we want to visualize the Big Bang is happening at a point, some cosmic egg that exploded and flew off in all directions. Of course, this would violate the cosmological principle, right? The cosmological principle is that the universe is homogeneous and isotropic, that there is no preferred place, there's no center, no edge of the universe. And if there really were a cosmic egg that exploded, the universe would have a geometric center. There would be a special point in space, which would be the center of that expansion. So the analogy I like to use in order to explain the expansion of the universe is think of a sheet, a flexible rubber sheet. And on that rubber sheet, we draw a grid of squares like I've drawn here on the screen. So you see that every square is exactly the same as every other square. And it doesn't take a lot of imagination to extend this sheet of squares, this uniform sheet of squares, infinitely in all directions. This is a good analogy for a geometrically flat cosmological spacetime, which in fact comes closest to describing the universe we happen to live in. We can measure the geometry of the universe. And as far as we can tell, we live in a flat geometry, which is exactly like this. To generalize this to 3 dimensions, of course, you would have an infinite space, an infinite 3-dimensional space carved up into identical cubes. This satisfies the cosmological principle because every point in this space-time, every place or every point in this space is exactly the same as every other point because every square is exactly the same as every other square. So now we take this infinite grid of squares and imagine it's on a stretchable sheet, like a sheet of rubber, and stretch it evenly in all directions so that all of the squares stay exactly the same size, or stay exactly the same as each other, but they all grow in size with time. So the squares get a little bit bigger, and that scale factor in the metric actually tells you the scaling of these squares as they get bigger and bigger and bigger. Notice this matches what we see in the universe, so that if we're sitting at at the intersection of any of these two lines, what we see is every other point, every intersection of lines on this grid is moving away from us, and the further away from us they're moving, the faster they're moving, the faster they're going. That's simply because there is more, the further away you are, the more space there is in between you to begin with, so that when that space expands, then your distance increases proportional to your original distance from the observer. Furthermore, this is true no matter where you're sitting on this grid. Everyone sees the same thing. Everyone sees themselves at rest in the center and everything else in the universe expanding away from them. So in this sense, the universe always has no center and no edge. It satisfies the cosmological principle. Every point in the universe is the same as every other. And we code expansion by just increasing and increasing and increasing the size of these squares as the expansion continues. Now, we can now time reverse this. We can say what happened at early times in the universe. And of course, if you time reverse this and plug it into Einstein's equations for gravity, what you find is that earlier on in the universe, the squares were smaller. All the galaxies and matter in the universe was closer together than it is today. And earlier and earlier, those squares were smaller and smaller, so everything was crammed closer and closer together. Earlier, still closer and still closer. And eventually, it turns out that when you actually plug it into Einstein's field equations, at finite time in the past, all of these squares went to zero size. So in fact, that grid collapses to zero size at a finite time in the past. We know how long ago that was, about 13.8 billion years, give or take. The experimental error on that is very small now. It's about 200 million years. And so and that's the moment that we call the Big Bang, the moment when all of the squares on this grid, when the density of the universe became singular, when the squares go to zero size, the density of the matter in the universe goes to infinity, and there's a singular point. Our laws of physics break down, and we can no longer apply general relativity. Notice that this singularity happens in an infinitely large space, right? The Big Bang doesn't happen at any one point in space. It happens everywhere in an infinite space at once. The Big Bang is spatially infinite, but what it is, so the universe, at no point in its evolution does it have a boundary in space, but the universe nonetheless has a boundary in time, and that boundary in time is that past singularity of the Big Bang. We can see this on a space-time diagram as well. So if we look at light cones in a Minkowski space, for example, in special relativity, we have our future light cone, which defines all of if we are here at this event P, our causal future is all of the points in space-time that lie inside that future light cone. And our causal past is all of the points in space-time that lie inside that past light cone. And everything that lies outside the future and past light cones that I've labeled elsewhere here is causally disconnected from this event P. There can be no cause and effect relationship from any of the between any of these points and this event in space-time. The point here is that in Minkowski space, or in special relativity, both the future light cone and the past light cone are infinite. Because the space is static, it has an infinite past and an infinite future. So this past light cone extends infinitely far into the past. Not so in a Robertson-Walker space. The difference with a Robertson-Walker space is, in fact, that it is not past finite. It has a cutoff at a finite past time. We can draw a similar diagram of future and past light cones in a cosmological space by doing a trick. And that trick is we take that metric that we wrote down for the Robertson-Walker space, where the spatial components had that time-dependent scale factor, and factor that scale factor out into a conformal factor in front of our metric. This is equivalent to saying all we're going to do is we're going to measure time using a clock that slows down with the expansion of the universe, which we call conformal time. So if we measure time correctly, what we find is that the Robertson-Walker space is conformally equivalent to a standard Minkowski space of special relativity, where we just have to measure time in this funny way according to the conformal time. The cool thing here is that we can now draw space-time diagrams with light cones, right? The light cone now is ds squared is equal to 0, which means that the conformal time is equal to the displacement in space. So photons travel in Robertson-Walker space on geodesics, where the d tau by dx is equal to 0, right? That you're traveling at the speed of light. So we can draw light cones in Robertson-Walker space as 45-degree lines, exactly as we would in Minkowski space. So locally, they're identical. The difference is that globally, they aren't. So here is a diagram of the past light cone in a Robertson-Walker space. And what you find is we're sitting here. This is us at the present. And as we look back in time out along our past light cone, our causal past is the region that is enclosed within this cone. But in fact, our causal past isn't infinite. The causal past in the Robertson-Walker space-time is sliced off at a finite time in the past, which is the spatially infinite surface of the Big Bang. So you can imagine a Robertson-Walker space being pretty much the same as a Minkowski space, except you chop it off with a cleaver at some finite past time and then say that nothing is allowed before this point. This is the basic causal structure of a Robertson-Walker space-time, locally identical to a Minkowski space, but globally what you have is that in fact it is not past infinite the way a Minkowski space is. It's actually chopped off at a finite past time. So now we start out with a universe at infinite density at the Big Bang, propagate it forward in time, and end up in the universe that we live in today. So how this universe evolves, question, yes.
Taka.
Hello? Okay. So how this universe evolves, the history of this universe depends on its contents. And there are three basic categories of contents depending on how they behave with respect to its expansion. So we call this a cosmic cocktail. I stole that term from a really excellent popular book by Katie Fries. The three main ingredients of the cosmos fall into three categories, basically. First is matter. So this would be baryonic matter like atoms, or dark matter, for example, the stuff that clumps under gravity. And imagine the behavior of this under expansion. Model this as just a bunch of particles, massive particles, or dust inside of a box. As that box expands, the particle number is conserved. So what we find is that the density of those particles is just inversely proportional to the volume of the box, a co-moving box that expands along with the expansion of the universe. So that means the density of the stuff in the box is proportional to 1 over the cube of the scale factor, right? Each linear dimension of this box grows proportional to A. So the density of matter inside the box drops proportional to 1 over A cubed. Contrast this to radiation, for example, photons and neutrinos. In this case, the number density of photons in the box drops as 1 over A cubed, exactly as in the case of dark matter, but there's an additional effect, which is that the photons redshift with expansion, they lose momentum. And so photons propagating through this expanding space-time lose momentum. Energy is not conserved in an expanding space-time because time translation and invariance is not preserved. And photons not only drop in number density, but each photon also loses energy as it propagates through this expanding space-time, which gives you an extra factor of the scale factor. So the energy density of photons in this space-time drops more quickly than matter in such a way that it goes as 1 over the scale factor to the 4th. The third ingredient of the cosmos, and one that was only fairly recently discovered, is vacuum, or energy of empty space. Since the volume of the empty space in a box, if you actually give space itself some sort of energy density, then since the volume of space increases exactly in sync with the volume of the box, that means that the energy density of vacuum energy inside the box doesn't change at all. It is constant. So in this way, we have three components to the universe, three basic components to the universe. Vacuum density, which doesn't redshift at all, doesn't change at all with expansion. Matter, which redshifts is 1 over a cubed, and radiation, which redshifts is 1 over a to the fourth. And we can measure the current composition of the universe. This is probably a familiar slide. That vacuum energy in the current universe, or dark energy, which is either vacuum energy or something very much like it, makes up 73% of the universe. Cold dark matter makes up about 23%, and baryonic matter, normal atoms, make up about 4%. This is a very curious recipe, and it reminds me of we'll get to that in a second. So, and at that point, what we find is that if we take the current composition of the universe and propagate that backward in time, we could create a sort of a timeline of the universe. And this has got a bunch of things on it that we're not going to really discuss in any detail in this talk, the quark-hadron phase transition and baryogenesis and nucleosynthesis and all this. But the point I want you to take here is that the universe is currently vacuum dominated. We're about 3/4 dark energy. But because the dark energy, if we turn this around and go backward in time, matter and radiation blue shift more strongly than the vacuum. So at an earlier time, between about when the universe was about starting when the universe was about 60,000 years old and ending when it was about 1 billion years old, the universe was actually dominated by matter, dark matter and baryons. And then prior to that, earlier than matter radiation equality, which was at a temperature of around 10 to the 4 Kelvin in the early universe, or before about 60,000 years after the Big Bang, the universe was actually radiation dominated. And so this gives you a rough picture of the universe, which is the very early universe was radiation dominated. It went through a phase transition at about a temperature of 10 to the 4th Kelvin, at which point it became matter dominated. And then at a temperature of about 5 Kelvin, the vacuum, which redshifts less slowly, became dominant, and the universe became vacuum dominated in the present universe. So this brings to mind a quote from the Castilian king and great patron of the sciences, Alphonse X of Castile, or Alphonse the Wise, who, among other things, was a patron of the Alphonsine tables, which was at the time the most accurate table of planetary motions that had been compiled, and also one of the first examples of big science in the medieval world. There were more than 50 astronomers from a variety of religious backgrounds in Spain that worked in Toledo on the creation of the Alphonsine tables. But Alphonse, speaking of the Ptolemaic system, and I think his words probably apply to the current cosmological, the lambda CDM cosmology that we favor today, was, if the Lord Almighty had consulted me before embarking on creation thus, I should have recommended something simpler. We don't understand why the universe is broken down into these components like it is, but it is, and we have to live with it. So how does this fit together in terms of the causal structure of the cosmology, right? So we have this history where the universe started out radiation dominated, matter dominated, and vacuum dominated. And furthermore, we know that the early universe was very hot and very dense, right? So if you take all the stuff in the current universe and pack it together, you end up with a hot, dense initial state. And cosmologists are fortunate because looking out in space is looking back in time, right? Telescopes are time machines. Because when we look back in time, we're looking back along our past light cone. The further out we look in space, the further back in time we see. And so as we look further and further out, we see further and further back into the early history of the cosmos. So we don't have to guess what the early universe looked like. If we can build a telescope that can see out 1 billion light years, we can see the way the universe was 1 billion years ago. If we look out 10 billion light years, we can see the universe the way it was 10 billion years ago, and so on. And so we can actually see the past, the universe when it was hotter and denser than it is today. And this brings up the idea of a horizon. How far out can we see in this infinite uniform universe? We can't see out forever because the universe has a finite age. because of the fact that the universe had a beginning about 13.8 billion years ago. And looking out in space is looking back in time. We can't see any further back in time than time zero. That means that we also can, there's a limit to how far out in space we can see. This is called the cosmic horizon. And basically this is, if we're sitting here, the distance out we can see, the maximum distance we can see out in the universe is, roughly speaking, up to expansion factors equal to the speed of light times the age of the universe. So when the universe is 1,000 years old, we can only see out about 1,000 light years. In fact, in a radiation-dominated universe, this is a factor of 2, so it would be 2,000 light years when you take expansion into account. When the universe is 1,000,000 years old, you can only see out 1,000,000 light years modulo an expansion factor. And so as the universe gets older and older, we can see further and further out. And this edge of the observable universe is referred to as our horizon. And in a matter-dominated or a radiation-dominated universe, this horizon gets larger and larger with time, and we can see further and further out. And we, at any given time, we only see an infinite patch, a finite patch of this infinitely large space, but that patch is growing with time, and we see more and more and more of that infinite space as time goes along. So for example, in this diagram, the second observer, the second person that I have diagrammed over here, would be outside of our horizon. One way to think of it is that if this were an observer on another galaxy, they'd be receding away from us faster than the speed of light, and we would be unable to see them. But gradually, as the universe evolves, we see more and more of the universe, and eventually this galaxy does falls into our horizon and becomes visible to us as our horizon gets larger and larger and larger. The point being that our horizon in the universe is finite. We can only, despite the fact that the universe is infinite at all times, all the way back to the Big Bang, we can only see a finite patch of it. Our observable universe extends only out to our horizon. Now notice that as we look outward in space, we look backward in time. And in fact, this circle of our horizon, if we could see that far out, if we could build a telescope that would see all the way out to our cosmic horizon, we would see the Big Bang itself. So instead of the Big Bang happening at a particular point in space that's somewhere out there, the Big Bang happened everywhere in space at once. But what we actually see when we look out at the universe is we see ourselves embedded exactly at the center of a spherical universe. And the outside boundary of that spherical universe is the moment of the Big Bang that we're seeing as we look out in space and look back in time. This boundary of the universe, the observable universe, is our horizon. This is a perceptual effect, right? It's just like the horizon on Earth. So two observers on Earth will see different horizons. And in fact, those two horizons may or may not overlap a little bit, but we only see a finite patch of the Earth because of the Earth's curvature. And someone standing somewhere else would see a different finite patch of the Earth because of its curvature. Similarly, in the universe, because of expansion, two different observers will have two different horizons, two different observable universes, even though the universe on the whole is completely homogeneous and isotropic. And our horizons may or may not overlap with the horizon of another universe elsewhere, another observer elsewhere in the universe. Another way you can visualize this is on a space-time diagram, is that if we look at our past light cone, where it is chopped off by this infinite surface of the Big Bang singularity, our horizon size is simply the size of our past light cone projected onto this initial singularity at time 0 in the early universe. This will be important when we talk later about the causal structure of this, and in particular the horizon problem and how difficult it is to understand the homogeneity of the cosmic microwave background. So I really love this picture, which is actually an accurate and to scale picture of the observable universe as seen from the solar system. So this is actually logarithmic in scale. So you're starting at the solar system and measuring distance logarithmically as you go out. This outer boundary of our observable universe is the Big Bang. The very early portions of it are when the universe was very hot and very dense before the formation of stars or galaxies, when the universe was an ionized plasma at thousands of degrees Kelvin. Eventually, the universe cooled to the point where neutral hydrogen condensed. The universe became dark, and before the formation of the first stars, we consisted entirely of warm neutral hydrogen that was expanding and cooling with the expansion of the universe. Eventually, stars began to form at cosmic dawn at the end of the Dark Ages. Structure in the universe formed, galaxies, clusters and galaxies, and so on. And eventually, the formation of the solar system happened 4 or 5 billion years ago, and we live in the center of this. So what we see is really, we see ourselves at the center of a spherical universe with the entire history of the universe into the past, all the way to the Big Bang, playing out as we go closer and closer and closer to the sphere of the edge of this observable universe. This is kind of remarkable in the sense that this is rather reminiscent of the Ptolemaic universe that was the subject of so much consternation by Alphonse the Wise. And in fact, we see that instead of the primum mobile, the sphere of the stars that bounded the Ptolemaic universe and separated the material realms from the ethereal ones, our primum mobile is not in fact the sphere of the fixed stars, but the sphere of the Big Bang itself that surround us at equal distances on all sides. This is a remarkably different picture of the universe than I think certainly a lot of laymen have. The thing is that when we look back, we look at out in space and back in time, we can't see all the way to the edge of this observable universe. We can't see all the way back to the Big Bang, at least not using photons. The reason for this is that the early universe was opaque, right? In fact, we can only see back to when the universe was about 300,000 years old, or at a temperature of around a few thousand Kelvin, which is the event of recombination. Any earlier than this, the gas in the universe was ionized and the universe was opaque to photons. The mean free path of a photon was very short compared to the Hubble length, the size of the horizon. And after recombination, the universe became transparent. So the limit of how far back we can see is this point at which ionized hydrogen condensed into neutral hydrogen, which is the event called recombination. Basically, this is a schematic diagram of this. So in the early universe, when the temperature was above about 3000 Kelvin, the universe was, the gas in the universe was hydrogen and helium were ionized in the early universe. Photons scattered rapidly off of the free electrons, and it would have been like being inside a glowing fog. And right about 300,000 years after the Big Bang, 380,000 years, and when the universe cooled below about 3000 Kelvin, these electrons were quite rapidly captured by the positively charged nuclei. And as soon as the universe became dominated by neutral hydrogen and helium, the universe was effectively transparent. The mean free path of a photon became of order or larger than the horizon size of the universe. And these photons began to free stream in all directions, leaving behind a relic gas of thermal equilibrium photons at a temperature of about 3000 Kelvin. Since then, the universe has expanded by a factor of about 1100. So that initially 3000 Kelvin gas of photons is a little bit less than 3 Kelvin today, about 2.7. And that residual gas of photons is the cosmic microwave background that we observe with radio telescopes today. So here is what we really see when we look out in space and back in time. Instead of seeing the sphere of the Big Bang, we are instead at the center of a sphere whose outer boundary is the glowing surface of last scattering when the universe went from being opaque to being transparent. So it's like looking at the underside of a cloud, except that it's a sphere surrounding us. And that cloud is emitting photons at a temperature that appears to us to be about 3 Kelvin. Furthermore, this primordial universe, the surface of last scattering, is completely uniform. The temperature of the cosmic microwave background is exactly the same everywhere on the sky to about 1 part in 100,000. The primordial perturbations, what you're seeing in this picture, which is the Planck satellite measurement of the variations in that temperature, these variations are on the order of a few microkelvin, or about 1 part in 100,000. So what we know, we can look at the early universe and see that it was incredibly uniform and incredibly homogeneous and in an extraordinary degree of thermal equilibrium, right? The cosmic microwave background is the best black body ever measured in nature. This actually is beautiful. The early universe was very simple. It consisted of 3 parts hydrogen, about 3/4 hydrogen, about 1/4 helium by mass, and a gas of photons. It was uniform to 1 part in 100,000. And these little temperature fluctuations in the cosmic microwave background correspond to fluctuations in the density of the matter of the universe. And as we know, these little fluctuations contain an incredible amount of information about the composition and the physical conditions of the early universe. But for right now, what we care about is that the early universe was extremely homogeneous. And in fact, this is not only, it is not explained by the standard Big Bang cosmology, but the standard Big Bang cosmology cannot explain it. It is fundamentally impossible for it to do so for reasons of causality. And this is where we bring in inflation. And I'll talk about this in the language of the horizon problem in a minute. But we know that the standard Big Bang cosmology has to be incomplete because the standard Big Bang cosmology does not explain how the cosmic microwave background achieved this incredibly high level of thermal equilibrium, unless you assume it as a boundary condition. Part 2, cosmic inflation and an infinity of worlds. So back to the primordial perturbations, right? These are homogeneous and isotropic. Why is this a problem? Well, let's look at our light cone diagram. So we're looking out into the past. When we look at the cosmic microwave background, we actually see out in space and back in time. So when we look at the CMB on one side of the sky, we're looking out along our past light cone, and we're looking far, far into the past when the universe now is almost 14 billion years old. We're looking back to when the universe was about 300,000 years old. So schematically, it's right about here. If we look at in another direction on the sky, we're looking out along our past light cone this way, and we're looking back to this point in our space-time along our past light cone over here, also to when the universe was about 300,000 years old. Now, if we draw the past light cones of those points, we see that they don't overlap. This point on the cosmic microwave background and this point on the cosmic microwave background have no causal connection to one another because of the fact that there was not enough time after the Big Bang for photons to travel from this point to that point. They're causally disconnected. Nonetheless, observationally, it's simply a fact that this point on the sky and this point on the sky are in thermal equilibrium, incredibly good thermal equilibrium to about 1 part in 10 to the 5th. Despite the fact that there's no causal connection, there's no way that this point and this point can have communicated with each other in the interval after the Big Bang. So that's the question, is how did they get in thermal equilibrium in the first place? Another way to look at this is to look at a blow up of the cosmic microwave background itself. So this is just zooming in on the Planck map. And if we look at this, if we take any point on the sky and say, what was the size of the observable universe of that point, as seen from that point on the sky at the time of recombination, that's 300,000 light years multiplied by an expansion factor. But if you work out how big that is on the sky today, it's a circle about 1 degree across. So what I've drawn here is for each of these points on the cosmic microwave background, the observable universe as seen by an atom that was sitting at that point at recombination would only be about that big. Nonetheless, all of these points, which are outside each other's observable universe, essentially in separate universes from one another, are in thermal equilibrium to 1 part in 100,000. So this is unexplained by the standard Big Bang cosmology, and this is one of the primary motivations for inflation. So how do we fix this? How do we create a causal structure such that it's possible for these points, all of these different points in the cosmic microwave background, to actually share a causal past and to reach thermal equilibrium with one another? The answer comes in vacuum energy. So what we look at is if we have a universe that is filled entirely with vacuum energy, something whose energy density with expansion stays constant in time, it's a simple matter to solve the Einstein field equations for the expansion of the universe. And what you find is that the scale factor expands exponentially, right? The universe begins to expand exponentially quickly. In fact, this is happening now. Dark energy, we are transitioning into an era of dark energy in which the expansion of the universe is approaching an exponential state, where h is the current expansion rate, the Hubble constant of about 70 kilometers per megaparsec, 70 kilometers per second per megaparsec. In inflation, what we do is we assume that there was a period in the extremely early universe, long before this hot thermal equilibrium state that we observe in the cosmic microwave background or even further back in primordial nucleosynthesis. And say at some point prior to nucleosynthesis, there was a period of vacuum domination and accelerated expansion. Why does this help? We can draw a horizon diagram just like we did before, except in an inflating space-time, it's different than what we saw before. In particular, in inflation, the size of the Hubble parameter, the expansion rate, stays roughly constant. So the size of our observable universe stays roughly constant. But the space-time itself, or the space itself, is expanding exponentially quickly. That means that the size of these squares is expanding exponentially fast, even though the size of our observable universe is nearly constant in time. What this does is if we take two observers who are initially causally in contact with one another, or inside each other's observable universes, inside each other's horizons, and expand exponentially quickly, what we find is these two observers are almost immediately stretched away from each other so that they are now outside each other's causal horizons. This is the mechanism that inflation proposes to bring the cosmic microwave background into thermal equilibrium. The idea being that if you have enough exponential expansion, you can start out with a causally connected patch that reaches thermal equilibrium through some other process, and then expands out, or at least is causally connected, and then is stretched by this exponential expansion out to extremely large sizes, where it then explains the homogeneity and uniformity of the universe on scales much, much larger than the horizon size, which is what we observe in the cosmic microwave background. So inflation solves the horizon problem by introducing a period of exponential expansion. We also get something else for free, which is that the universe the inflation makes the universe, drives it toward geometric flatness. We observe that the universe today is extraordinarily close to geometrically flat within a few percent. And inflation gives you this for free, because you can imagine that if you're on a strongly curved space-time, and then you leave the size of your observable universe alone, but stretch the size of that space-time out exponentially large, that curvature gets smaller and smaller and smaller, and the curvature of any local patch on that universe becomes incredibly tiny, and our observable universe, as far as we can tell, is exactly flat. So inflation does two things. It causally explains the homogeneity of the universe on scales larger than the horizon size, for example, at the time of last scattering. And it also provides a dynamical explanation for the geometric flatness of the universe. Neither one of these things are explained in the standard LCDM cosmology. So here's a causal diagram of how inflation solves the horizon problem. In fact, now what we thought of as the surface of the Big Bang, which was the onset of this hot thermal equilibrium phase, this radiation-dominated phase of expansion in the early universe. In fact, that was not the beginning of the universe at all. It was at only the end of this inflationary epoch. So what we do is we replace that initial singularity in the standard Big Bang cosmology with the end of this other period of exponential expansion, the end of inflation. And then we have this enormous sea of time below that, in which these past light cones of for example, on the cosmic microwave background, have time to overlap and actually become causally connected. And then we can explain the thermal equilibrium of the CMB by purely causal processes. Here's the thing. We can't just use a cosmological constant to do this, because inflation has to end, right? We have accelerating expansion here. We have radiation domination, and decelerating expansion happens here. We know that the early universe was radiation dominated, at least as early as primordial nucleosynthesis. So there has to be some transition. There has to be some dynamics. So we can't just have a cosmological constant, a uniform vacuum energy density, because then inflation would never end. We have to have dynamics. We have to have a vacuum energy that actually has dynamical characteristics. So how do we do this? Well, particle physics comes to the rescue, and it comes through the process of symmetry breaking. That's familiar, for example, from the Higgs boson. And here's an analogy for symmetry breaking that I like to use, which is, imagine a pencil balanced on its tip. It's unstable, right? If you have a pencil balanced on its tip, it's going to fall over. But notice that if you balance that pencil perfectly at a point where classical physics tells you that it will just remain upright forever, right? We know that because of instability, it won't. But that has a symmetry in that you can rotate that pencil around its axis, around the vertical, and in fact, you'll get the same thing back. So the pencil standing on its tip is rotationally symmetric. Now imagine the pencil falling over, right? You break that rotational symmetry, because no matter what direction the pencil falls, it picks out a direction in space. So that in fact, you have a transition from an unstable symmetric state, one with a rotational symmetry. Gravity means that that thing is unstable, the pencil is going to fall over, and then that eventual state with the pencil falling over in some particular direction picks out a direction in your space and breaks that rotational symmetry. This is a nice analogy for the Higgs boson, because we can note that the upright pencil has a certain amount of potential energy. The pencil sitting on its side has less potential energy. And so what we can do is we can plot the potential energy of that pencil as a function of how far it's tipped from the vertical. And because of the fact that it doesn't depend on what angle the pencil tips in, it's a surface of rotation that ends up looking like this familiar sombrero shape, or the Mexican hat, which is the standard symmetry breaking potential. It looks exactly like the potential for the Higgs boson, right? So at the maximum of the potential energy is when the pencil is sitting upright, and then as the pencil tips, the potential energy drops and drops and drops, and eventually it drops to a minimum when the pencil is lying on its side. This is the idea of symmetry breaking. And so we can take any symmetry breaking process, whether it's a ferromagnet or a pencil standing on its tip or the Higgs boson, and draw the symmetry breaking as a surface of potential energy as a function of whatever configuration is relevant for the problem, whatever order parameter there is for the transition from the symmetric to the asymmetric state. And it's physically relevant for a pencil. It's actually directions in space and rotational symmetry that we're breaking. So we have two possible states, right? A state with the pencil upright and a state with the pencils falling. Now, if we want to generalize this to something like the Higgs boson is a field that permeates all of space. So a nice analogy for symmetry breaking in the Higgs is, in fact, think of the Higgs as being a bunch of pencils all balanced on their tips, filling all of the space in the entire universe. And that we represent that as a little ball sitting up on top of the hill of this potential surface. Now, when the Higgs goes through the electroweak phase transition and the particles in the standard model acquire mass, what happens is that the symmetry is broken everywhere in space, and furthermore, it's broken everywhere in space in the same way, analogous to these pencils all falling over in the same direction and picking out a preferred direction in space. In the case of the Higgs boson, it picks out a preferred direction, not in physical space, but in an abstract space of field theory, but the principle is exactly the same. So we have every pencil, every point in space, this Higgs boson has a potential energy, which means that it acts like a vacuum energy, right? This is exactly the kind of thing we talk about when we talk about a vacuum energy. When you have a scalar field in an unbroken symmetry, then the potential energy of that scalar field fills your entire space-time. And that potential energy filling your space acts like a cosmological constant. But the cool thing here is that we've now added dynamics to this, that we can have that cosmological constant disappear by a symmetry breaking phase transition where the ball rolls down the hill. And now that potential energy, that energy of empty space-time, that vacuum energy disappears in the symmetry breaking phase transition. And so we're going to steal this idea from particle physics, which was stolen from condensed matter physics, and apply it to cosmology and apply it to the physics of the early universe by speculating that in the early universe, inflation, this accelerating expansion in the very early universe, was driven by a scalar field in an unstable equilibrium that later on went through a phase transition. That energy density disappeared and in fact decays into particles in the standard model and creates the onset of the radiation dominated universe that then creates the hot Big Bang subsequently. So here's a schematic diagram of this. When you have a symmetry breaking phase transition and when the field is up here near the unbroken symmetry, the energy density of this is given by the kinetic energy of the field plus the potential energy. Because of the fact that the universe is expanding so rapidly, and the potential in this case is very, very shallow, very, very flat, that the kinetic term of this is subdominant. The field is very slowly rolling. The expansion of the universe actually creates a drag term on this. So as it evolves down the potential, as it starts to roll, the expansion creates a drag term and inhibits it. So it's not just a ball rolling down a hill. It's more like a ball rolling down a hill through a tub of molasses, where that molasses is the drag created by the expansion of the universe itself. So what you see is that the energy density of the scalar field is dominated by the potential energy, and it acts exactly like a cosmological constant. It acts like vacuum energy and drives exponential expansion. Finally, when the field rolls further down the potential and it gets steep, then the field starts to roll more quickly, starts to oscillate around the bottom of the potential, and the accelerating expansion ceases, and the universe enters a phase of decelerating expansion. And furthermore, if you assume that this field is coupled to the other fields in the standard model, this oscillating field about the minimum will decay into standard model particles. It will heat the universe up into a thermal equilibrium state in a period called reheating, and you end up with creating the initial conditions for the hot Big Bang, some extremely high temperature, and then subsequently you have radiation-dominated expansion following that. We don't know the form of the inflationary potential. It could very well be this kind of symmetry breaking potential that we've been talking about that looks like this. Or this potential surface could be one in which the symmetry doesn't break, in which you're simply rolling down, displaced from the bottom of a hill, a bowl, where the symmetric state is your stable equilibrium, and you have a field rolling down like that. And we can talk a little bit about the observational distinction between these two things a little bit later. But this potential in principle can take any shape that you want. There's no fundamental reason it has to be one thing or another. And different shapes for the potential give you different expansion histories for the universe and different basic physics, and also give you different observables, which is one of the key points, is that you can actually tell the difference between this and this by looking at observables such as the cosmic microwave background. Why is that? How does this relate to observables? That's because the inflaton, this field that is rolling down this hill, right? So inflation happens when you're up here near the maximum of the field and slowly rolling. Inflation ends when you roll down and the potential becomes steep. So you explain this early period of acceleration followed by a late period of radiation domination. But this is a quantum field, right? So it doesn't just undergo classical evolution, it undergoes quantum evolution as well. So there are little quantum jitters in this field. You can think of the quantum effects as just this field bouncing back and forth along this potential. Quantum effects will cause the field to roll out, jump down the potential a little bit, or even jump backwards, jump up the potential a little bit. This couples the field to the density of the spacetime, to the curvature of the spacetime. When it jumps up the potential, the density of the spacetime and the expansion rate are a little bit higher. When it jumps down the potential, the density of the spacetime and the expansion rate are a little bit lower. So these quantum fluctuations that are happening at all scales, these little 0-point fluctuations due to vacuum energy, in the vacuum energy due to the Heisenberg uncertainty principle, are creating little density fluctuations in the universe. When it rolls up the field, you get a little overdense region. When it rolls down the potential, you get a little underdense region. And so classically, the universe stays exactly perfectly homogeneous and isotropic. But when you add quantum fluctuations in, there are these tiny little anisotropies, these overdense and underdense regions that are created by the quantum fluctuations. Furthermore, because of the accelerating expansion, these little quantum fluctuations are stretched from very short wavelengths to very long wavelengths. They, like anything else, like any other wave phenomenon in the universe, have wavelengths that stretch proportional to the scale factor. So if this thing has a wavelength of exactly 2 squares wide, it stays 2 squares wide, even when those squares are exponentially expanded to larger than the observable universe. So you have tiny little quantum fluctuations on sub-horizon scales that are almost instantaneously stretched out to wavelengths that are larger than the size of the observable universe. At which point they cease to become quantum mechanical. They actually become, technically speaking, they're a squeeze state. More colloquially, they just become classical. So these are imprinted as classical fluctuations in the background spacetime. These are actually fluctuations in the curvature of the spacetime, which are represented as fluctuations in the density of the matter later on in the universe. So you find that when you solve the horizon and the flatness problems for free in inflation, you get something else that you hadn't necessarily bargained for. When you include quantum mechanical fluctuations, you also explain those tiny little inhomogeneities. Those 1 part in 10 to the 5th fluctuations in the cosmic microwave background are explained as relics from the inflationary period, these relic curvature perturbations that were stretched out, quantum fluctuations during inflation stretched out to superhorizon scales and then are frozen in the background. And those are what create the perturbations in the density of the universe that you see in the temperature anisotropy of the cosmic microwave background. Here's a quantitative picture of this. This is actually a quantum mode as it's being stretched out by inflation. So this is increasing wavelength as you go from left to right. And what you see is that when the wavelength is small, the horizon size is right here, this green line. What you see is when the wavelength is smaller than the horizon size, the quantum mode is oscillatory. When it gets stretched larger than the horizon size, the oscillations cease and the wave equation just becomes a growth equation. And what you find is that the amplitude of this mode doesn't get driven to 0 as it gets stretched outside the horizon, but actually goes to a constant. So these quantum modes, this is called mode freezing, these quantum fluctuations actually freeze out as classical perturbations in the universe, much larger than the size of the horizon during inflation, and then gradually fall back into the horizon as the universe expands. So in this way, inflation explains the primordial perturbations, right? So these fluctuations we see in the CMB, you can actually take an inflationary potential, crank through the quantum mechanics, and calculate what the cosmic microwave background ought to look like. And in fact, what you find is that the perturbations in the cosmic microwave background are matched very nicely by the predictions of inflation. They have a nearly scale invariant power spectrum. They're adiabatic, which means that they all of the different components of the universe have overdensities that are in phase with one another. There are super horizon-sized correlations. The temperature of these fluctuations is actually correlated on scales greater than the horizon size at the time of last scattering, which is something that is extraordinarily difficult to explain without inflation, these kind of super horizon correlations. And you have a prediction from inflation that you're going to see both density perturbations, which is what you see in the CMB, and also gravitational wave fluctuations, which have yet to be detected, but could very well be within reach of future observational measurements. I'm not going to dwell too much on the observational side of this in this talk today, but I just want to emphasize that this picture, this quantitative picture of quantum mode generation actually does an incredibly good job of explaining not just the qualitative features of the cosmic microwave background, but actually quantitatively very precisely matches what we see in the CMB. Inflation is by any measure a superbly successful theory, a predictive one, and has passed a number of non-trivial observational tests. I want to spend a moment talking about the consequences of this for the global structure of the universe, however, which is that we have this picture of the inflaton undergoing quantum fluctuations and classical fluctuations. But the faster the expansion rate, the larger the quantum fluctuations. So the amplitude of the quantum fluctuations is determined by the expansion rate, by the Hubble constant. So the faster the universe is expanding, the bigger the quantum fluctuations. Similarly, with respect to the classical fluctuations, the classical motion of the field, because the expansion drag, the drag on this field caused by the dynamical drag on this field caused by cosmological expansion is also proportional to the expansion rate. And that drag increases as the expansion rate increases as well. So what you find is that as the higher the Hubble constant is, the higher the density of the universe or the expansion rate, the larger the quantum fluctuations are and the smaller the classical motion is. These add up in the same direction. So if the universe is expanding fast enough and the potential is flat enough, if the slope is gradual enough and this field is rolling slowly enough, the quantum fluctuations will actually start to dominate over the classical ones. And what happens here then is that the field will jump up the potential as often as it goes down the potential, and you'll have an infinite number of regions of space that will never actually roll all the way down the potential, and inflation will end. You have a competition between two rates. The classical evolution, which drives inflation down the hill and ends inflation in reheating and a radiation-dominated universe. And the quantum fluctuations, which actually drive you back up the field and make inflation go on for longer and longer. If you do the calculation of this competition of rates, you find that the expansion of the universe is so big that you actually end up exponentially dominated by regions that are still inflating, and regions where the classical evolution has taken over and inflation ends are actually only happens in very isolated localities in the universe. So this gives us a picture of the universe on the largest scales as something like a glass of beer, where you have bubbles nucleating inside your beer. So you look at you take a glass of beer, you have little bubbles that form inside that via a phase transition, right? Very similar to the phase transition associated with inflation or with the Higgs boson. Except that now in our cosmological glass of beer, the beer itself is this region, is the inflating region where you're still in the false vacuum. And the bubbles after you've gone through the phase transition are the ones that are in the true vacuum. And these little bubbles where inflation ends are being pushed apart from each other exponentially quickly by the expanding region in between, and they never have time to percolate. So you're creating space in between these bubbles exponentially quickly, but these bubbles themselves are only growing at about the speed of light. And so what you have is immediately you have this idea of an inflationary multiverse where you have an infinite number of these little bubbles of true vacuum in this eternally expanding space-time. Inflation goes on forever and continually produces more and more and more of these bubble universes. And we just happen to live in one of these little bubbles. And the larger cosmos as a whole is mostly a sea of continuing inflation and we're causally separated from all these other bubble universes and can't even in principle observe their existence. Now, the cool thing is that inside, from the outside, if we're looking at this from the point of view of a glass of beer, these little bubble universes appear to be finite, right? So you nucleate a bubble, and in the case of inflation, this bubble nucleates and starts expanding outward at the speed of light. But because the space-time is expanding faster than the speed of light, these bubbles never run into each other. And so you have a situation something like this, where you have this bubble expanding in space and time. So as the bubble expands outward at the speed of light in space, it traces out a light cone, a forward light cone in time. The cool thing here is that we can refoliate the space-time. We can redefine space and time by making our space-like hypersurfaces a hyperbola that's nested inside this forward light cone of the bubble. And what we see here is that if we refoliate this, if we change our definitions of space and time, the space inside this bubble that appears finite to an outside observer is actually infinite in spatial extent to someone sitting inside the bubble. So in fact, what we do is we have an infinite amount of time, and we borrow some of that infinity of time and create a spatially infinite universe inside the bubble, so that time is now perpendicular to the bubble wall, and spatial hypersurfaces are along these hyperbolae that are nested hyperbolae inside the bubble. And we see that we can take this finite bubble in this inflationary multiverse and nest a spatially infinite universe inside that bubble, where the end of inflation is the bubble wall, which is everywhere in our past. So now this is the point at which we made the transition out of the eternally inflating phase into the classically inflating phase, and then eventually inflation ends and we enter a radiation dominated universe. And so what we see here is that each of these bubble universes inside this glass of beer contains a spatially infinite, causally separated inflationary universe like the one we live in. And this is the picture of the inflationary multiverse that is pretty much an inevitable consequence of the theory of inflation itself. So going back to Giordano Bruno, this is really Bruno's idea of an infinity of worlds writ large. So Bruno in 1584 wrote, "Thus is the excellence of God magnified and the greatness of his kingdom made manifest. He's glorified not in one, but countless suns, not in a single earth, a single world, but in 1,000,000, I say in an infinity of worlds." And inflationary cosmology takes Bruno's infinity of worlds and extends it out to an infinity of universes. And we are but one of an infinite group of causally disconnected universes whose existence we can never verify in any scientific way at all. In fact, this takes us really beyond what we would even call a well-defined scientific theory, and is something that is essentially an unfalsifiable conclusion, but it's an inevitable conclusion of the laws of physics that we put down to explain this inflationary expansion, to explain the homogeneity and isotropy of the universe itself. So this is a good stopping place. I can talk a little bit about quantum gravity and the swampland. I'm not sure exactly how much time I have left in my talk, but I would be happy to stop here if this makes a pretty good 1 hour talk right where it is. So I'm happy to let the audience decide on that one.
Okay. Yes, we are on time.
We are about on time, so why don't we just leave it at that.
We have time for questions.
Okay.
From the audience. Lautaro Labarca.
Hey, Professor. Thank you. Hey, Professor Lautaro, Professor William. Thanks a lot for the talk. It was super fun for me. I never studied anything about cosmology before, so it was super fun for me. And I have some questions, very simple questions, actually. So the first question I have, you mentioned earlier that vacuum energy remains constant, the density. So right now, at this precise moment, vacuum energy is increasing in our universe. That's my question. The total vacuum energy.
The total amount of vacuum energy, right?
Yeah, the total.
Is that what you're asking about? Yeah, it is.
Okay.
So
okay.
that seems to violate conservation of energy, doesn't it?
Yeah, seems weird, but.
Yeah, well, it does violate conservation of energy.
Okay. Okay. So the notes. Okay. Okay.
It's like conservation of energy just doesn't hold. And so in fact, right, if you look at a co-moving box, right, so let's go back. Okay, so I have stopped. Let's go back to this box of vacuum, right? So let me share my screen. Let's see. Where is, there's Zoom, open Zoom, back to meeting, share screen. Okay, so here, our box of vacuum, right? So the density of energy inside this box is a constant, right? But this box is increasing with expansion. So if I look at a co-moving box and I say, what's the total amount of energy in this thing, right? And then I look at the total amount of vacuum energy in this box later on. In fact, it has increased by the volume, by a factor proportional to the volume of the box, right? So the total energy in that box has actually gotten bigger.
Mhm.
This does not violate local conservation of energy, right? Remember, general relativity takes global energy conservation and replaces it with a local energy conservation law, stress energy conservation. That is, general relativity says that the amount of energy flowing across the boundary of this box has to match, that the amount of energy flowing out of the exterior region and flowing to the interior region have to match each other, right? That's a local conservation law. But what that means is if no energy flows across the boundary, you can still increase the total amount of energy inside the box by expansion.
Mhm.
So it's sort of a loophole in GR that, in fact, there's only a local notion of conservation of energy, which means that you can globally violate conservation of energy as long as nothing is flowing across the boundary of the box. And in the case of vacuum energy, that's true. There's no flow across the boundary.
Okay, fantastic. So how does that compare to the energy that's lost in the photons? Like in that box, in the second box, gave it started at the left, right? And
Yeah. Right. So in the case of the photons, it's that extreme. So this depends essentially on the equation of state of the matter is the way it's mathematically normally prescribed. But in this case, the number density of photons in the box is conserved, right?
Mhm.
So you can think of it the same way as with matter. The number of particles in the box stays the same. If you think about it with photons, then the total number of photons in the box doesn't change, but their number density goes down as 1/a cubed. But then that energy drops down by a little bit more because they're redshifting. So the energy per photon is also dropping by a factor of 1/a.
Mhm.
So photons redshift very quickly relative to matter or radiation. Does that answer your question?
Yeah, no, my question is like if I take the energy, for example, I take the box at the left and I take the box at the right, and I adapt the energy of the vacuum plus the energy of the photons. So which box has more energy, the one to the left or the one to the right?
In this case, if you have it in the case of radiation dominated expansion, where it's just mostly photons, right? The box in the right actually has less energy in it. It's
Okay,
lost energy instead of gaining it.
okay,
But once again, no energy has flowed across the boundary. That energy has just disappeared into nowhere. It hasn't gone anywhere else.
okay.
Right.
Thanks.
So this also violates conservation of energy, but it doesn't seem as counterintuitive as vacuum energy, at least not to me.
Fine. Yes, I just wanted to know what the state of it. What do we know about it?
Right.
So
So in the case of photons, the box loses energy. In vacuum, the box gains energy. In the case of matter, the total energy in the box remains constant. Right. So the total number of particles and the total mass, the total amount of mass in the box stays constant. So the total amount of energy stays constant.
So yeah, so at some point, I guess, if we use imagination, at some point, I guess, vacuum energy will start, if it keeps increasing at the same pace, as the total space keeps increasing, I guess that fallout of the energy of the photons is going to be so small at some point that the vacuum energy is going to begin increasing, and then the
Right.
global energy is going to start increasing once again, right?
So vacuum energy erases everything else.
Yeah.
And that's really kind of the beauty of inflation, is that whatever happened before the start of inflation, right, this period in the very early universe, we don't understand the initial conditions for inflation at all. All we can see in the cosmic microwave background in the relics is the very end of inflation.
Okay, thanks. I had another question. Sorry, my bad. It was about, I just wanted to clarify something that I always hear and I don't understand is, what do you mean when you say the universe is almost exactly flat? Like, what does that mean in a more precise way?
Well, it means that basically you can measure the curvature of a spatial surface by its geometry, right? So for example, if I draw a triangle on a flat Euclidean plane, right, all the angles in that triangle will add up to 180 degrees, right? This is the standard result from Euclidean geometry, right? But if I draw that same triangle on the surface of a sphere, right, the angles of that triangle will add up to more than 180 degrees because the surface of that sphere is curved, right?
Mm-hmm.
Similarly, I can have a hyperbolic space in which I can draw a triangle in which the angles add up to less than 180 degrees.
Okay.
So we can actually measure the geometry of the space-time. Right? So if we can draw a big enough triangle in space, in the universe, we can actually measure the angles in that triangle and see whether they add up to exactly 180 degrees or more or less.
Okay. Okay. That's
And
pretty
it
cool.
turns out that they add up to exactly 180 degrees. The spatial slices of the universe, constant time spatial slices of the universe, are exactly Euclidean.
Okay. Okay. That's fantastic. Thank you. Thank you. I didn't know that. Thank you. I have a question, but I think it's fine when you have more people. Thanks a lot.
You're welcome.
Okay, Lautaro. There is another question from Simon Riquelme. Simon?
Yes. Hello, Professor.
Hello.
Hello, Professor. Can you help? Can you hear me?
Yes, I can hear you great.
Okay. Well, thank you for the nice talk, by the way. I have two questions.
Sure.
First one would be, you know, you always hear about the horizon problem, and basically that being, you know, kind of like a starting point for thinking about inflation. But that's related with causality, right? So in some sense, if you abandon causality, maybe you can find another way of dealing with this problem.
Absolutely.
So can you tell us a little bit about you know, approaches like that use some kind of an entanglement picture for trying to deal with this?
Yes. There are a number of people who have proposed various ways to get around those causal limits. For example, a very well-known one is by João Magueo, looking at variable speed of light. So the idea being, if the speed of light was higher in the early universe and lower today, then you could create this apparent homogeneity in the universe by having a variable speed of light. I have also worked on models that we call tachyacoustic models, in which you have non-canonical field theory. Turns out that if you do, you can construct scalar field theories with non-canonical kinetic terms, such that they have a speed of sound that's superluminal. So you actually have the sound waves in the scalar field propagate at faster than the speed of light. This doesn't violate any of the restrictions in relativity because it's essentially a superluminal ether, right? So you have the universe filled full of a fluid that has a speed of sound faster than the speed of light. Turns out that you can avoid any causal paradoxes. You don't have closed time-like loops. You can't travel back in time until you kill your grandfather or anything like that. But what it can do is create this homogeneity, and actually, and you can also come up with models that in detail will give you that scale invariant spectrum of perturbations that you see in the CMB. So these are a couple of ways that people have come up with trying to use violations of standard relativistic causality in order to explain this. These models have a variety of problems. In particular, it's very difficult to construct them in such a way that you don't end up requiring cosmological densities that are much higher than the Planck density. So they typically don't work as well as inflation.
Okay.
But people have proposed such things where you have superluminal propagation, for example, as a way to explain this.
Okay, thank you. And the second question I have is that is basically, what would you say if I told you that you know, I have this geometric inflation theory, which only has basically the degrees of freedom of Einstein gravity, right?
Right.
Just as massless spin 2, nothing else. And I tell you, this gives you inflation and everything we observe. I have my own standing about that phrase, but I would like to know about yours. My understanding is that basically we do need a scalar degree of freedom in order to account for the primordial.
There's a reason for that. And the reason is just simple quantum numbers, right? So vacuum energy, anything that's going to act like a vacuum energy, right? Anything that's going to act like a cosmological constant has to have the same quantum numbers as vacuum. It has to be spinless, right? So you either have to figure out, if you have like a spin 1, spin 2 field, you either have to take one component of that field and turn that into the vacuum energy, or you have to have a scalar. What you do is, if you, for example, had a vector field that you just tried to use as the inflaton, you'd violate isotropy. You'd create anisotropic cosmologies because there'd be an inherent direction in there. There are inflation models that are constructed, for example, out of spin 1 fields, out of vector fields, and so on. I mean, there's been a lot of work done on that. But basically what you do is you use vector condensates that create an effective scalar degree of freedom, and that gives you your vacuum energy. So that at the end of the day, it still acts like a scalar. The way I like to put it is that the inflaton, this field, whatever it is that is responsible for creating the vacuum energy, need not be a fundamental field. Right? If you think about it in terms of a phase transition, right? A pencil falling off its tip or a ferromagnet or anything like this, that the field, that thing that you plot on the potential surface, is just an order parameter for some other physical process, right? So it could be a phase transition of, in some sort of condensate. It could be, for example, in string theory, it has to do with the compactification of the extra dimensions and branes moving in compactified dimensions. So the physical identity of the inflaton field in different fundamental theories is going to be wildly varying. The only thing that you need is to have essentially a single order parameter that governs the vacuum energy, that governs your position on that potential surface, regardless of what the underlying physics is. So it doesn't have to be a fundamental field like the Higgs boson. It can just be an order parameter for some more complicated process. That's totally fine. Does that help?
Yes, of course. But so basically, you do need a new scale, at least one new scalar degree of freedom. You cannot just do it with a massless spin 2. So
not in standard GR. I mean, if you wanted to modify gravity in certain ways, you could do it, right? But then once you transfer that into the Einstein frame, you're going to end up with a scalar tensor theory, right? So for example, one of the models that fits the data best right now is a model that was proposed in like 1982 by Starobinsky, which is actually a modified gravity model in which you have a square of the Ricci curvature. The action is R squared instead of R. When you transform that into an effective GR theory, when you take that and transform it into the Einstein frame, what you end up with is GR plus a scalar sector with an exponential potential. So typically, if the underlying physics is some sort of modification of gravity, that it's actually coming from a general relativity-like theory. When you reduce that to an Einstein frame action, you typically end up with scalar degrees of freedom that are then driving your inflation. So it's just like I was saying, it's just an order parameter for some more complicated physics. That physics could very easily be gravitational in nature if you wanted it to be. And there are plenty of theories in which that's true.
All right. Thank you very much.
Thank you. Thank you, Simon. Perhaps we have time for one more question. If no, then I will thank again William for this wonderful talk.
Thank you very much for inviting me.
Thank you very much. And I want a last word I like to say, because Professor Kinney has written a book that will appear next year, as far as I know, about cosmology.
Oh yeah, let me plug my book here. I think I have a slide with the cover on it. Here it is. So let me share my screen with my cool book slide. Just a moment. There's the cover. So yeah, this basically I've written a popular level book. A lot of the slides that you just saw were actually figures that are from the book itself. It's a popular level explanation of inflation, multiverse, observational constraints on inflation, the whole 9 yards. It will be out on March 1st, 2022. And you can pre-order it on Amazon right now or on your favorite bookseller. So it's available globally. And just about any online bookseller will have it available for pre-order at this point. So please drive my numbers up and pre-order my book. You'll like it. Thank you.
Mm-hmm. Thank you very much. Thank you for all of you, and you are invited for the next seminar here. Thank you again, Will.
Thanks very much.
we're talking.
So, Professor Lautaro,
Yeah,
can I make a super quick question? I-
we have run out of time, Lautaro. Sorry.
Okay, no problem.
Bye. Bye. Bye.